Now, today, we'll continue studying the centripetal force and circular motion. And, and we will continue solving the problems. In the previous lesson, we solved some problems which the object is moving in a vertical circle. But this time, there are some chapter 2 questions. We are going to solve them. The objects are moving in a horizontal circle on a horizontal surface. The first question is question number 33 in chapter 2 question, page 28 in the textbook. Question is this: 13,500 Newton car traveling at 50 km per hour around a curve of radius 2 times 10 to the power of 2 meters. Find the centripetal acceleration of the car. The part A is asking about finding centripetal acceleration. So we are going to use the equation for centripetal acceleration, which is AC is equal to VT squared over R. But VT, tangential speed, in here is given in kilometer per hour. This is tangential speed, but kilometer per hour is not a SI unit. That's why we should first convert kilometer per hour to meter per second. After that, we should continue solving. And the radius of the curve is given. So this car is rounding a curve, something like this. So this curve has a radius which is equal to R 200 meters, which is 2 times 10 to the power of 2. Find the centripetal acceleration of the car. So if we know VT, if we know R, we can calculate centripetal acceleration easily. So VT is 50 km per hour, R is 200 meters, so we will calculate what centripetal acceleration is. But first, we have to convert kilometer per hour to meter per second. The basic method is this. This is kilometer in numerator and hour is written in denominator. So first write 1 kilometer is equal to 1000 meters in numerator. 1 hour is equal to 3600 seconds, write it in denominator. After that, use your calculator. 50 multiplied by 1000 divided by 3600, you will get the result as 13.6 meter per second. So we converted the kilometer per hour to meter per second. And then we can use the equation for centripetal acceleration. So VT squared over R. VT, right now we calculated 13.9, square of 13.9 divided by the radius of the circle is given as 200 meters. So if we divide them, we will get the centripetal acceleration as 0.97 meter per second squared. This is part A. The problem has a part B, so keep this acceleration in your mind because we will use it in the second part. In part B, find the minimum coefficient of static friction between the tires and the road that will allow the car around the curve safely. In fact, this part B is giving a hint about which force is allowing this car to move on a circular path. It is the friction. So, but we are not going to calculate friction force. We will calculate coefficient of static friction between the tires and the road. So when a car is moving on a circular path, so there will be 3 forces acting on the car. One of them is gravitational force, Fg, down. So a second one is normal force, up, because normal force is always perpendicular to the surface. Surface is horizontal. That's why normal force is in vertical. And each force, both forces are perpendicular to radius of the circle. That's why they cannot be effective on centripetal force. And the third force is the static friction force, and we know that static friction force is always parallel to the surface. Surface is in horizontal, that's why static friction force must be in horizontal. And we know that static friction always acts in the opposite direction of the tendency of an object, in which direction it will slide. We are going to apply this or draw the static friction force in the opposite direction. So this force is the static friction force, and static friction force is pointing the center, so it's the only centripetal force in here. So we will say that force of static friction is the centripetal force that maintains a circular motion of the car, and then we are going to make static friction equal to centripetal force. Fs is equal to Fc. And next step is write the equation for Fs and Fc. Fs is mu s multiplied by Fn. You are going to calculate static friction force by multiplying coefficient of static friction by normal force, and Fc is equal to mass of the object multiplied by centripetal acceleration of the object. So then we know that if the object is on a horizontal surface, yes, this car is moving on a flat surface, horizontal. So Fn and Fg are equal to each other. That's why instead of Fn, you can write equivalent of Fg. So equivalent of Fg is mass times gravity. So we insert it instead of Fn mg. And then we are going to see that both sides of the equation has m, and m will simplify. And then you are going to get mu s times g is equal to ac. After that, simplify g on the left side because we are going to calculate what mu s is. Simplify g as well by dividing both sides by g. So we will calculate mu s as ac divided by g. So this is the equation for calculating coefficient of static friction. So we can say that this is in fact a general equation. This equation is a short way. If your surface is horizontal, yes, like this, horizontal surface, and the circle is horizontal, circle of the followed by the object is horizontal, mu s is the static friction force, is the centripetal force, and mu s is going to be calculated by centripetal acceleration divided by free fall acceleration. So centripetal acceleration we calculated in part A 0.97, free fall acceleration 9.81. When we divide them, we will get the coefficient of static friction between the tires and the road as 0.1. As I said, this equation always correct if an object is moving in a horizontal circle in contact with a horizontal surface. So if a car is making a turn on a horizontal surface, if a bicycle or a bike making a turn on a horizontal surface, always mu s is equal to ac divided by g, centripetal acceleration divided by free fall acceleration. So we are going to use in some problems, we can use in some problems directly this equation for calculating mu s. Next problem, question number 34. Question number 34 is very similar to 33. That's why I will skip it. It's just asking about the speed. Vt is asked, but mu is given. Opposite of that, in here, speed is given, but mu s is asked in question number 33. In question number 34, mu s is given, but Vt is asked. That's why you are going to use the same methods for calculating what mu s is. That's why I will skip this. You can try it on your own. We have one more problem. This problem is much harder compared to other problems in the first two questions. A copper block rests 30 centimeters from the center of a steel turntable. So this table is able to rotate with some angular speed turntable. And a copper block rests 30 centimeters from the center of the steel turntable. This is the copper block in here, and this copper block is resting at 30 centimeters from the center. So this distance is given as 30 centimeters. And the coefficient of static friction between the block and the surface is 0.53. Mu s is given in this question. So r is 30 centimeters, 0.3. Mu s is coefficient of static friction between the block and the surface is 0.53. The turntable starts from rest, so initial angular speed is 0, which means from rest means initial angular speed is 0, and rotates with constant angular acceleration. So here is an acceleration, angular acceleration is given as 0.5. So 0.5 radian per second squared is the angular acceleration, which means this turntable is starting from rest and speeds up by time. After what time interval will the block start to slip on the turntable? If you rotate this turntable with small angular speed, you are going to observe that this copper block will follow on a circular path like this at different times. But when this turntable starts moving faster and faster and faster at some angular speed, some critical angular speed of the turntable, this copper block will leave the turntable. So we will find what is that maximum final angular speed. First we should get it. After that we are going to use kinematic equations for calculating how long does it take reaching from rest to that angular speed. So delta t is the question, but first we should calculate at what maximum angular speed it's going to be, in fact, final angular speed. So we'll first find that. The block is still moving in circular path without slipping. We should get it. In fact, method is the same. First, force of static friction is the centripetal force. We will make them equal. Static friction force is the centripetal force. Static friction force equation mu s times Fn, which is equal to mass times AC. Which is Fc is equal to mass times AC. Fn is equal to Fg because the surface is horizontal. Fg is down, Fn is up, so Fn and Fg cancels, so they are equal. So I'm going to write instead of Fn equivalent of Fg, which is m times g. Mac is equal to r times omega squared. Just I want to find that final speed. What is that maximum final speed? Still keeping the block on the circular path. So we should get this first. M and M will simplify, and then by dividing both sides of the equation r, because we need to get what omega final is, we should simplify r. So that's why we should divide equation by r. This r also will simplify. We will get omega squared as mu s t divided by r. After that, get the square root of both sides of the equation. Omega final, that omega final, we are going to calculate that maximum speed. The copper block is still following circular path, is going to be calculated by root of mu s g over r. And now insert a mu s. Mu s is given as 0.53, and g is 9.81, r is equal to 0.3. When we insert them all, we are going to calculate what is the final angular speed. But you don't need to, in fact, to do all these steps. That short equation, mu s is equal to AC over g, can help you to get what omega final is. So you can start from here as well, because horizontal surface and the copper block is moving in horizontal circle. So this equation, mu s is equal to AC over g, holds for this example as well. AC is r omega squared divided by g. So you will calculate what omega is. So cross product r omega squared is equal to g times mu s. After that, divide by r both sides. Omega squared will be mu s g over r. And after that, you will get, in fact, the same equation. This and that equations are the same. So we are going to insert the given into the equation, and we will calculate the omega. So mu s is equal to 0.53, g is 9.81, and then the radius of the circle is 0.3. So angular speed of the copper block, of course, together with the turntable, is going to be 4.16 radian per second. So this, at this angular speed, is the maximum angular speed of the turntable and copper block, still keeping the copper block on this circular path. If speed becomes a little greater than that value, so this copper block will not stay on the circle, it will move off the table. So then next step is, how long does it take for this copper block to attain that speed? We are going to use kinematic equation. So remember, kinematic equation, we are going to use this an accelerated motion. Alpha is equal to omega final minus omega initial divided by delta t, definition of the angular speed. So just we're going to calculate delta t. That's why we're going to cross product. Delta t is going to be omega final minus omega initial divided by alpha. So omega final is 4.16. Initial is because it starts from 0 divided by alpha, angular acceleration 0.5. So you will calculate delta t as 8.32 seconds. So it takes 8.32 seconds for this this copper block. So for 8.32 seconds, it stays on the on the turntable without slipping. But after that time, so because angular speed becomes greater than 4.16 radian per second, so it cannot follow circular path. It's going to be off the table. And we have one more question, but this question is a bit different than the previous one. Now, in the first two questions we solved, surface was horizontal, contact surface was horizontal, but objects are following horizontal circle as well. But now in here, in question number 36, it will be a bit different. In a popular amusement park ride, a cylinder of radius 3 meters is set in rotation at an angular speed of 5 radians per second as shown in figure. The floor then drops away, leaving the rider suspended against the wall in vertical position. What minimum coefficient of static friction between the rider clothing and the wall of the cylinder is needed to keep the rider from slipping? Now this is the cylinder. Inside this cylinder, there is a person standing. This cylinder has a radius r is equal to 3 meters. It's a huge cylinder, and it's rotating with an angular speed of 5 radians per second according to the question. So then the floor drops away, which means this floor will move down, fall down like this. So it falls down, but this rider, this person, will stay suspended against the wall. It will not fall down. So, in fact, questions giving a hint again. Why is it like this? What is the minimum coefficient of friction? Friction force, of course, is holding this body on the wall. What minimum coefficient of friction between a rider's clothing and the wall of the cylinder is needed to keep the rider from slipping? Now, in fact, this movie is showing how this system is working. Now I'm going to show it to you. They are inside a cylinder, and this cylinder is spinning. Let me make the sound slower, volume smaller. Okay, then continue. Yes, they are spinning inside a cylinder. They are children. Now they are standing on the floor. However, as angular speed gains enough, the required value or that specific value, so this floor on which they are stepping will be taken down. It will taken down, but these children will stay suspended on the wall. Now look at the, so it's just right now, yes, as you see, now they are just suspended on the wall in here, so because friction force is keeping them on the wall. So the case is that, so how is it possible? Now we are going to study the physics of this now. Okay, let's do this. In fact, the case is this. In here, when the children is against the wall, children is in contact with the wall of the cylinder, of course, pushes the wall of the cylinder outward. I mean, as the cylinder rotates, the rider, the child inside the cylinder pushes the wall of the cylinder with Fn prime, but we know that if this is reaction, the cylinder's wall will give a reaction on the rider's body. So this is also known as the normal force, which is perpendicular to contact surface. The contact surface in here is now in vertical. Normal force is now, as you see, in horizontal. So Fn will be acting on the rider's body. And of course, gravitational force will act downward towards the center of the Earth. Only if gravitational force and Fn would be acting on the rider's body, so this rider will slide down. So there must be a force which stops this sliding. Of course, that force is going to be static friction force, and we know that static friction force is always parallel to contact surface. A contact surface is vertical, that's why static friction force must act in vertical. But in which direction, downward or upward? Of course, it will act in the opposite direction of the tendency of the skidding. So this body tendency of skidding is downward, so the static friction force must act on rider's body upward. So rider stays suspended on the wall because static friction force cancels gravitational force because they are equal in magnitude and opposite in directions. So if we draw the picture, it's going to be this way. Three forces will be acting on the rider's body. One of them is the Fn by the wall, so reaction force by the wall. Second one is gravitational force. Third one is static friction force between the wall of the cylinder and rider's body. And rider is following a horizontal circle. Now, surface is vertical, but circle is in horizontal. So this is different than the previous questions. In the previous questions, surface was horizontal, circle was horizontal, but this is completely different. Now, question, which force is pointing the center of the circular path? So Fn. Fn is acts in horizontal, and that Fn points to the center of the circular path, followed by the rider's body. That's why Fn is the only centripetal force in here. So we are going to make Fn is equal to Fc. Normal force is acting on the rider's body, is the only centripetal force acting on this rider. So Fc, we can write it by m times AC. So Fn is equal to m times AC. So according to the centripetal force equation. But in vertical, this body stays suspended. If the body stays suspended, because Fg and Fs must cancel, so to cancel, their magnitude must be equal. So I'm going to write Fs, static friction force, which is upward, must be equal to Fg, gravitational force, which is downward. Then write the equivalent of Fs and Fg. Fs is equal to μs times Fn, and Fg is equal to m times G. Now we are going to insert this Fn into that because they are the same thing. They are defining the same Fn. I am going to write equivalent of Fn. Equivalent of Fn is mass times AC. I will insert this mass times AC into this equation right there. So I will write equation μs m times AC, which is equivalent of Fn, is equal to m times G. These two m will simplify again. We will get the equation μs AC is equal to G. And after that, divide by AC, because you are going to calculate μs, divide by AC. So you will get μs as AC G divided by AC. G divided by AC is the equation for calculating μs. This is opposite of the first case, horizontal. When the surface is horizontal in this question, let's go back. In this question, when the surface is horizontal and the circle is in horizontal, so μs would be calculated centripetal acceleration divided by free fall acceleration. But in this question, when the surface becomes vertical and the circle is in horizontal, μs becomes free fall acceleration divided by centripetal acceleration. What is the equivalent of centripetal acceleration? R times omega squared. Insert R and omega and G into the equation. You are going to calculate the coefficient of friction between static friction between the rider's clothing and the wall of the cylinder. And this was the last chapter of question, and then we finished it. Now we are going to solve some section rule questions. First question is question number 1, page 24. A roller coaster moves through a vertical loop at constant speed and suspends its passenger upside down. This position in here. In what direction is the force that causes the coaster and the passenger to move in the circle? This is asking, in fact, what is the direction of the centripetal force? And we know that if it suspends passengers upside down, I mean the car must be up in here at vertical position. So let's draw in another color. So right here, the car is up there. So that's why the center of the circular path is here, and we know that centripetal force always points towards the center. That's why the force that causes coaster and passenger to move in a circle must be downward. So answer of this sentence, this question is going to be downward. And what provides this force? There are two forces acting on the roller coaster. One force is absolutely gravitational force, always acts downward and pointing the center of the circular path. Let's show with another color. In here is the center. And Of course, this car is roller coaster car is in contact with the track. Of course, there must be an action reaction forces between the track and the car. So this roller coaster car pushes the track upward, and track gives reaction downward, which is Fn. So Fn is also pointing towards the center. So both are pointing towards the center. Both are positively affects the centripetal force. That's why we are going to say that force of gravity is one force which provides centripetal force. Second one is the normal force by the track. Normal force by the track also affects the centripetal force. So if we want to write the centripetal force equation at this point, it's going to be Fg plus Fn, because both are pointing the center of the circle. So we are going to add them. So resultant force will be the centripetal force acting on the car at that position. And next question is about a bicycle and bicyclist. Identify the forces that maintains the circular motion of the following. A cyclist moving around a flat circular track. So first, I'm going to show you a movie. While a cyclist is moving around a flat circular track, so how their body is aligned relative to the ground. Let's see it and then watch motion. When their body is inclined, of course the cyclist is in contact with the bicycle. So but the contact surface between the rider, between the cyclist and bicycle, is all the contact surfaces are inclined. I mean, his seat is inclined, his handle is inclined, foot is inclined. If the surface in contact with the cyclist is inclined, so normal force also must be inclined. These are the normal forces acting on cyclist. And this normal force now will provide a centripetal force because it's inclined. If it is vertical, if it were vertical, in this case, normal force would not give a contribution, but because bicycle becomes inclined, normal force also becomes inclined, and this normal force provides a centripetal force for cyclists. And one more force exists between the rider and the bicycle, which is the friction force, of course, static friction force between the seat and the rider's body. This friction force also provides centripetal force, and in short we can say that the forces that the seat, handlebars, and then pedals exert on the bicyclist, and these forces are friction force and also normal force. Even the horizontal component of these forces, which is pointing the circular path, will provide the centripetal force. But if we are talking about the bicycle moving around the flat circular track, we are going to think about the combined mass of the bicycle and the rider. So there are three forces acting on this combination. One of them is, of course, gravitational force always acts downward, and gravitational force acts perpendicular to reduce. That's why gravitational force in here cannot be centripetal force. Second force is the normal force between the tire and the ground. Ground is horizontal, that's why normal force right now in vertical, perpendicular to reduce. This normal force also cannot be centripetal force. Just one force is left, which is the static friction force. Static friction force always parallel to contact surface, so surface is horizontal. Static friction force also must be in horizontal and in the opposite direction of direct tendency of the skidding. Tendency of the skidding is away from the center. That's why static friction force must point towards the center. That's why static friction force in here will be the only centripetal force which provides circular motion of the bicycle, of course together with the rider. And last question is identify the force that maintains circular motion of the following. So a bobsled turning a corner on its track. So let's see what's happening as bobsled is making a turning a corner by this move. Let me make this small. It's very loud. bobsled, which make traces on the ice. When bobsled is making the turn and turning a corner, so as you said, it's climbing a vertical wall. The wall is vertical right here. Bobsled is turning about this corner, and in this case, there will be two, four, three forces acting on bobsled. One of them is the gravitational force down. The second one is because there is some knife under the bobsled. It makes some traces on the ice, and then a kind of static friction acts in opposite direction of the tendency of skidding. And normal force, of course, by the wall. This wall applies a no reaction force because bobsled pushes the wall of the track, and then the wall of the track gives reaction on the bobsled. This reaction force, which is normal force by the wall, points the center. That's why this Fn is the only force which is pointing the center of the circle. It's going to be only centripetal force acting on this bobsled. And the last part is how inertia and circular motion are related. I'm going to briefly explain this one. First, we know that in the absence of a resultant net force or net force, a body will preserve its state of motion, which is known as Newton's first law of motion. What does it mean preserve its state of motion? So if it is at rest, it will stay at rest. If it is initially in motion, so it will move with constant velocity. We are going to study this in chapter 2, section 2, in equilibrium. So this is what we are going to talk about. So if initially somehow some forces is applied on the object and then set object into motion, after that, that force is released, this object will move with constant velocity. Constant velocity means object will follow a straight line path with the constant speed. So this is known as Newton's first law of motion, also known as law of inertia. And inertia is defined in the 11th grade as the tendency of an object not to accelerate, which means if object is at rest, so its tendency is to stay at rest. If object is in motion, its tendency is to move on a straight line path. If no net force acts on a body, tendency of the object is to follow straight line path. So consider a ball is attached to a string and swing. If there is no string, and then if you give some speed to this ball in this direction, horizontal, so this ball will follow this horizontal path till the end. But because this ball is attached to a string, this string applies a force, which is the tension force, and of course this tension force or string counteracts this tendency. Object in the natural tendency of the object is to follow the straight line path, but because you attach this ball by a string to a point, this string applies a force on the ball and causes a change its direction, and then that's why the ball gains a centripetal acceleration. So as long as this a sufficient centripetal force acts on this ball will continue moving on the circular path. So this is the key idea. As long as a sufficient enough, which means sufficient means enough, as long as great enough centripetal force acts on an object will move on a circular path. However, if centripetal force is not enough, somehow it becomes small, or angular speed increases, and then that's why centripetal force cannot be enough. What's going to happen if centripetal force is not enough? If it is vanished, like just in here, as this man releases, as soon as this hammer is released, so initially when this man is holding the hammer and then rotating the hammer on a circular path, however, as soon as he releases the hammer, yani centripetal force vanishes, so this hammer will not follow circular path. Instead, it will follow a straight line path, or it's going to leave this circle on a straight line path tangent to the circle. So there are two examples in the book about this. One of them is this. Consider a ball is whirled in a vertical circular path. So if the string breaks when the ball is at this position, at position A right here, so tendency of the object is to follow a straight line path tangent to the circle. So it's tendency of the object to follow tangential velocity at that point. So then the ball will move vertically upward, and the motion of the ball will be that of a freely falling body. It will move up and back down again. But if you break the string at this position when the ball is at the top of the circular path, so again the tendency of the ball is to move along a straight line path tangent to the circle. So the ball will fly off horizontally in direction tangent to the circle like that. So, but because of the gravitational acceleration of the Earth, a gravitational pull of the Earth, this ball will follow a parabolic path. So, which means if is great enough centripetal force is provided on an object, so object will follow a circular path. But if you are not going to apply a great enough centripetal force on an object, object will not follow circular path. Instead, it will leave the circle in a straight line path tangent to that circle. A good example for this one is a car turn. As the driver makes a sharp left turn, the passenger slides to the right and hits the door. What causes the passenger to move towards the door? This is the one question. So, in fact, this is also related to this case. If centripetal force is great enough, so of course we should know what centripetal force is in here. As the car and the car, before the car enters the turn, the car and the passenger both are following a straight line path. But as the car travels along the curved path, so if it is not so sharp turn, if it's a soft turn, so as car is turning, static friction force between the passenger's body and the seat, if this is enough static friction force is applied on the passenger's body, this passenger will turn together along with the car. So static friction force between the passenger's body and the seat will provide a centripetal force, and because this centripetal force is enough as the car making a soft turn, so the passenger and the car can turn on a circular path. But if the car makes a very sharp left turn, so just like this, in this case a static friction force between the passenger's body and the car seat will not be enough to keep the passenger on the circular path. That's why passenger will follow because of inertia along a straight line path. However, car is still turning. Car is making the turn to the left. So as car is turning to left, because passenger is moving straight line path, passenger will slide from the left side of the car to the right side. So the passenger slides away from his initial position and approaches towards the door. Eventually, passenger encounters or hits the door. As soon as the passenger hits the door, so of course passenger will apply a force on the wall which is action. Wall will give a reaction. A second door, an additional force will appear or will be applied on passenger's body. The door provides the reaction force, which is the normal force, as an additional centripetal force to enable